All right, if we have acetic acid and ammonia, this is a weak acid, weak base solution. So it's a weak acid, weak base mixture. Buffers are weak acid, weak base mixtures. So is this a buffer? Actually, this is a buffer. This is a buffer because, as we'll see later, the weak acid and the weak base don't completely neutralize each other out, and so we have a stable mixture of acid and base. And that's what we want. It is a buffer, but it is not a Henderson-Hasselbalch buffer. Buffer, but not Henderson-Hasselbalch. And so we can't use this equation. So, for example, if we try to use the equation pH is equal to pKa for acetic acid, plus the log of the base to acid ratio. The base in this case is ammonia. The acid is acetic acid. This fails. Why does it fail? It fails because they're not conjugates. You know, this pair, these have to be conjugates. And so they aren't conjugates. And so how are we going to solve this? Let's say I want to know the pH of this particular mixture. Okay, how would I solve this for pH? So what I'm going to do is I'm going to do the same thing I did for 16 and whatever else. And Petrucci is going to do it differently because Petrucci is going to say, oh, we don't need this step, or we can skip that step and do this. But what we're going to do is we're going to do the same kind of pattern. And the same kind of pattern is we're going to take the strongest acid plus the strongest base mixture. Did we already do this reaction? The strongest acid present is acetic acid. What's the strongest base? Ammonia. And so if we have a mixture like this, strongest acid plus strongest base. So what's going to form here? What's going to form is acetate and ammonium form. And so we want to know, what is the K for this particular equation? And so can you just look at it and tell me what equations you'd have to add up to get this? Did we already do a Hess's law style addition yet or not? Yeah? And so this is the same thing. We're going to try to figure out the K's by adding up equations that we know. One of them we know for acetic acid is Ka. And so this would be the Ka for acetic acid. And then we also know the Kb for ammonia. Gives us ammonium and hydroxide. This is the Kb. So what happens if we add these two equations together? Then we're going to get closer because we're going to get HAC plus ammonia plus 2 waters. This is going to produce hydronium plus acetate plus ammonium plus hydroxide. Still not quite there. We have too much stuff in here. We got to get rid of the waters. We got to get rid of the hydronium and hydroxide. And so, yeah, if we think about this, we could add the reverse of Kw. So if we do hydronium and hydroxide, this will give us 2 waters. H2O liquid plus H2O liquid. And this is Kw. And so what I'll do is I'll just add this equation here. The K for this is just Ka for acetic times Kb for ammonia. Didn't I see earlier that Ka times Kb is equal to Kw? Do you remember that? Ka times Kb is equal to Kw. And so does that mean that this K for the sum of the first two reactions is equal to Kw. Because I have Ka times Kb. And the answer, yeah, the answer is no. Why? Yeah, they have to be conjugates. This only works for conjugate pairs. Acetic and ammonia are unrelated. But the hydroniums cancel, the hydroxides cancel, the waters cancel, and that leaves me with HAC plus NH3. This is going to go to AC minus plus NH4 plus. K for this reaction is going to equal, well, the Ka for acetic, I know. The Ka for acetic is 1.0 times 10 to the minus 5. 1.8, sorry, 1.8 times 10 to the minus 5 from the book. The Kb is also given in the book, and it's 1.8 times 10 to the minus 5. Acetic acid and ammonia, by coincidence, have the same K value to 2 sig figs, but they're unrelated. Just by coincidence, they have it. To 3 sig figs, they probably aren't the same. But one way to think about this is acetic acid and ammonia are kind of equal and opposite in terms. One's the acid, the other's the base, and they kind of have equal strength in opposite ways. And then Kw is 1.0 times 10 to the minus 14, which gives us a K value of .24 times 10 to the 4th. It's kind of big. 3.24 times 10 to the positive 4. So it favors the product here. So what we do next is we just plug in the concentrations here. The concentrations, let's do 0.100 and 0.100 molar. So the initial acetic acid concentration, 0.100 molar, 0.100 molar. This is going to be 0 molar and 0 molar. And there's going to be a change, and then we're going to have some equilibrium concentration. So this is going to equal the acetate concentration times the ammonium concentration divided by the acetic acid concentration and the ammonia concentration. Well, it's not going to go to completion, so it's going to be minus x molar plus x plus x. We'll have 0.100 minus x, 0.100 minus x, x, and x. And so we'll get, on the top, we're going to get x times x is x squared. On the bottom, we're going to get 0.100 minus x quantity squared. I don't think the simplifying assumption is going to work so well here. Why? Because of k. K is kind of big, right? In fact, you know, if I gave it some thought, I probably wouldn't have started with this initial. I probably should have done what? Reset it. But I lucked out. How did I luck out? I lucked out because the math is not terribly difficult. And so I'm not going to reset it, but I should have reset it, right? Should have reset it. But got lucky because math is okay. If the math turned out to be difficult, I would one back and reset it and then tried the simplifying assumption. But here I already know the simplifying assumption is going to fail. I mean, I look at that K value, it's times 10 to the positive 4, which means it's mostly product. Well, there's much more product than there's reactant. That means we're going to have significant reaction to form it. But it's okay, because I'm going to go with this. I'm going to just take the square root of both sides. You know, we reset it to make the math easier, but the math is easy enough here. And we can solve for x. So if I take the square root of both sides, I'm going to get the square root of 3.24 times 10 to the positive 4 is equal to x over 0.100 minus x. So let's do that. 3.24 times 10 to the positive 4, the square root, that's 180. This is 180 is equal to x over 0.100 minus x. And so I'm going to get 18.0 minus 180x is equal to x. 18.0 is equal to 181x. X is equal to 18 divided by 181. 0.09944. 0.09944. So going back over here, it's going to be 0.100 minus 0.09944, which means I'm going to get 0.00056 molar here. In other words, if you look, how much of it did we lose? We lost 99.44% of it. That's a huge change. Simplifying assumption for sure would have failed. We should have reset it, but again, I don't need to. 0.0056 molar here, and then over here I'm going to get 0.09944 molar and 0.09944 molar. And now I want to double check my K, so let's just make sure. So I'm going to go 0.09944 squared divided by 0.00056 squared is equal to 3.15 times 10 to the 4. 3.15, that's 3.24. Did I make a mistake? It's off slightly. I mean, this rounds to 3.2, that rounds to 3.2, so it's acceptable. They both round to 3.2, but it's off a little bit more than what I would have expected. Maybe I should have carried some extra digits. Okay. All right, now what? Well, I see what's left over, and I just take the strongest acid and react with the strongest base. The strongest acid, what's left over, I have some acetic acid and ammonia left over. I could react those, but it's going to lead to the same thing. I could take the acetate and ammonium, react those together. This is already described in this equilibrium. And so what I do is I look for the next strongest. That is, now I have a mixture of all these species here. And so what should I do next? Well, basically all those species can hydrolyze water. So let's take a look at that. Let's look at, I have some acetic acid left over. That's the strongest acid present. And that acetic acid is already reacted with ammonia. And so I'm going to have some acetic acid left over in this mixture. And so the acetic acid will hydrolyze water, H2O liquid, to produce hydronium and acetate. And so I could do an ice table for this. But I also have some ammonia left over. And the ammonia can hydrolyze water to produce ammonium and hydroxide. That's a Kb. I have an ice table for that. The Ka for this is 1.8 times 10 to the minus 5. The Kb for this is 1.8 times 10 to the minus 5. Then I have some acetate and some ammonium present. And so the acetate plus water yields acetic acid and hydroxide. And the ammonium plus water yields hydronium plus ammonia. So I have this one. This would be the Kb for acetate. This would be the Ka for ammonium. So I can plug in all those concentrations and then solve the ice tables for these. But before I do that, take a look at these equilibria. Let's say, take a look at the top two equilibrium. What do you see? They're the same, right? So that means I could do one or the other. Which one should I do? It doesn't really matter, but I could do one or the other. You typically choose to do. Yeah. In fact, if I look at the bottom two equilibria, what do I see there? The same. If I look at the bottom two equilibria, I see the same. Bottom two are the same. And so how am I going to deal with this? Well, now I just have to deal with two equilibria here. And how I deal with that is this. The hydronium and the hydroxide are not independent of one another. And so if I solve these separately, I'm going to run into a problem because the hydronium and the hydroxide might not be mutually compatible. And so what I have to do is I have to do Kw, and basically I have to do this simultaneous. In fact, I could have skipped all that stuff. If I had a 0.100 molar acetic acid, weak acid, and a 0.100 molar ammonia, I would recognize this as weak acid, weak base combo. A weak acid, weak base combo like this that are not conjugates of one another must be solved simultaneously. And so we do Ka, Kb, and Kw solved simultaneously. And so I could have skipped that initial reaction because I would have been back to where I started. You know, back to where I started was just the acid and the base in water. And so this is it. Whereas if they're conjugates of one another, then it makes the problem much easier. And so we're going to take a look at an example of where they are conjugates. So this type of buffer is very difficult to solve. The pH for. How about this one? You know, if we take sodium monohydrogen phosphate and sodium dihydrogen phosphate, take 0.100 molar of each. Which one did we do earlier? We did sodium monohydrogen phosphate, is that correct, or sodium dihydrogen phosphate? For the amphoteric, do you remember that? Monohydrogen phosphate. So when we did sodium monohydrogen phosphate, that turned out to be a tough problem. You know, it's just sodium monohydrogen phosphate in water. Why was it tough? Because sodium monohydrogen phosphate is amphoteric. It has a Ka equation and a Kb that we have to solve simultaneously with Kw, just like acetic acid and ammonia. Well, this one's tougher, right? Because not only do we have one amphoteric, we have two amphoterics. So if we have two amphoterics, then does that mean we solve two sets of Ka, two Kas, two Kbs, and Kw? So altogether 5 equations, 5 ice tables simultaneously? It turns out, no. It turns out that, yes, this is amphoteric, and this is amphoteric, but when you mix them together, then they're no longer amphoteric. When we mix these together, sodium monohydrogen phosphate is no longer going to be acid or base, it's just going to be the, which one do you think? In other words, sodium monohydrogen phosphate is just going to be the base. Why? It can't be the acid because there's a stronger acid present. If there's a stronger acid present, that's the acid that's going to react. And so sodium dihydrogen phosphate will be the acid. Sodium monohydrogen phosphate will not. Sodium monohydrogen phosphate can't be the acid because there's a stronger acid that's going to lose its proton first. Sodium monohydrogen phosphate will be the base. Sodium dihydrogen phosphate cannot be the base either because there's a more powerful base around. And a more powerful base will react first. And did we already do this combination? Oh, so I already talked about this. Yeah. But we don't have to do all that because we should recognize that this is a, yeah, these are conjugates, and therefore this weak base, weak acid combination is called a Henderson-Hasselbalch buffer. And so far we've talked about a couple of weak acid, weak base combinations. One was the amphoteric, and the amphoteric we had to solve simultaneously. 2 was the weak acid, weak base combination that were unrelated, like acetic acid and ammonia. That we have to solve simultaneously. But fortunately, this one, we don't. Have to solve simultaneously. We just pick Ka or Kb, and in this case we pick Ka and solve the Henderson-Hasselbalch. And so let's take a look at HH buffers. HH buffers, the Henderson-Hasselbalch equation works. pH is equal to pKa for the acid plus the log of the base over the acid concentration. There's something called the optimum or the ideal pH. The ideal pH is when we have equal amounts of acid and base component present. That is, if we have equal concentrations of base and acid, then what we say is that this has equal capacity to neutralize added acids and added bases. And so if I have this mixture here, if I add some HCl, which of these two bases will attack? Only this one. If I add some HCl, this base will attack the HCl and neutralize it. If I add some sodium hydroxide, this acid will attack that. Now, if I have equal concentrations of both, then I have equal capacity to neutralize acids and bases. Sometimes I don't have. If I have unequal concentrations, then it'll be lopsided. For example, I have greater capacity to neutralize added acids versus added bases, or vice versa. When we have these equal, then the pH is going to equal the pKa plus the log of, it's going to be a 1-to-1 ratio. In other words, the pH will equal the pKa when the base and the acid concentrations are the same. But they don't have to be the same. We have something called the buffer range. The buffer range is going to equal the pKa plus or minus 1. And so this will give decent capacity still, but it's going to just be slightly lopsided, not severely lopsided. And so the limits plus or minus 1 come from this. If I look at the base to acid, I'll just call this the base to acid ratio. If I look at the base to acid ratio, and I have a 10-to-1, like this, and then look at the pH, which is going to equal the pKa plus the log of the ratio. And so this is just going to give me the log of 10, so the pH is equal to the pKa plus the log of 10 to 1, which is equal to pKa plus 1. Or if I have a ratio of 1 to 10, then that will give me a pH equal to pKa plus the log of a 1 to 10 ratio, which is minus 1. So this is pKa minus 1. If I go beyond that and make this even more lopsided, let's say I'm going to go to 1 to 100. If I go to 1 to 100, then the pH is equal to the pKa minus 2. And so this would be a much more lopsided base. And so this would be like, okay, I'm going to have 100 molar acetic acid and 1 molar sodium acetate. Can you even make 100 molar? No, it's too concentrated. And so we'd have to make it smaller. If we make it smaller, like 1 molar acetic acid, then the sodium acetate would have to be 0.001. And so it's quite lopsided. You have high capacity in terms of the acid component, but extremely low capacity in terms of base component. And so between these two limits is the buffer range. So what we can do is we can make adjustments in the ratio here. And when we make adjustments in the ratio, that changes the pH. And as long as we don't go too far and make the ratio too lopsided, then we're okay. The buffer should work. And so let's look at an example here. We're going to figure out how to make a pH 7.00 buffer. So we want a pH 7.00 buffer. How do we make it? All right, so if we want a pH 7.00, then we look for an acid with a pKa about 7.00. If the pKa is 7.00, then that means the Ka is around 10 to the minus 7. And so we're looking for an acid with a Ka around 10 to the minus 7. let's see what we have for choices. So let's take a look. So we're looking for K around 10 to the minus 7, 10 to the minus 6, 10 to the minus 7, 10 to the minus 8, around there. So acetic won't work, you know, because acetic, what we'd have to do is we'd have to make it way too lopsided, because the pK is around 5, K is around 5, and we want a pH of 7. It's going to be 2 power units, 100-fold. So we're going to have to put one component 100 times bigger than the other, which isn't so great. And so acetic's not, acrylic is not good. This is from Appendix D, by the way. Arsenic is, oh wait, dihydrogen arsenate. Dihydrogen arsenate's perfect. If we use dihydrogen arsenate, and this would be the acid, what would its conjugate base be? What's the conjugate base of dihydrogen arsenate? Monohydrogen arsenate. So if we put dihydrogen arsenate and monohydrogen arsenate in a 1-to-1 ratio, we would get a pH of 7.00. Perfect. And so this is perfect. At least the pKa is perfect because the pKa is 7.00. But it's not so perfect in terms of practical applications because arsenic acid and dihydrogen arsenate and monohydrogen arsenate are highly toxic. And so this is not a great buffer because it's too toxic. pK is perfect though. pK is just the power of the Ka, the negative power of the Ka. So let's skip that. Arsenous acid is also toxic, but it's way out there. We don't need that. 5, 3, 5, 7. Here, this is close. Carbonic. But there's a problem with carbonic. Can you go out and buy a bottle of carbonic acid? No. You know, you could. I mean, soda or club soda. But what's going to happen? This is going to decompose into water and CO2 eventually. It's going to go flat. So forget it. I'm going to do that here, even though it's close. 4.4 times 10 to the minus 7. We keep trying. Here, citric acid won't, dihydrogen citrate, monohydrogen citrate will. That's pretty close to 7. And so we could use monohydrogen citrate as the acid, and what would be the conjugate base of that? The conjugate base is not shown here. What would the conjugate base? Citrate ion. But we aren't going to use that because this is an organic acid. And some organic acids are electron rich, which means that they're prone to oxidation, being electron rich. And citric acid is one of these. Citric acid eventually will decompose due to oxidation. And so we want something that has a longer shelf life. There are ways to protect citric acid from oxidation. You could add antioxidants or whatever else, but we don't want to do that. It's too much hassle. We'll keep looking. Oh yeah, there's one. Good one. Hydrosulfuric acid. Perfect again. If we took hydrosulfuric acid, the acid, and mix it with the base, in this case the conjugate base is hydrogen sulfide. So we'll take some hydrosulfuric acid, H2S, and mix it with some sodium hydrogen sulfide in a 1-to-1 mole ratio. We got it. This will be perfect. Except, do you know about H2S, hydrogen sulfide? It smells bad. It smells like rotten eggs. Not only does it smell bad, it's extremely toxic. And this is lethal at the part per billion level. And so we can't use it. And so 2 of them were perfect, but we can't use those. Hypochlorous is close. You know, this is about 3 times 10 to the minus 8. If we go to 10 times 10 to the minus 8, that would be 1 times 10 to the minus 7. So this is very close. But hypochlorous acid is bleach. Bleach stinks, and it's also kind of volatile, the gas. So it's not a used bleach. We could use this. This is very close, because if we go to 10 again, 10 times 10 to the minus 8 is 1 times 10 to the minus 7, which would be perfect. So this is close to perfect. But what the heck is this? This is hyponitrous acid. Have you ever heard of hyponitrous acid? Since you probably never heard of hyponitrous acid, it must be expensive. And so we don't want it. Even though it's close, it's probably, too costly. And so let's skip that. Malonic, but malonic suffers from the same problem that citric acid does. It's fairly electron rich. It's easy to oxidize this stuff. You know, it'll eventually oxidize and decompose. Go down. Nothing. Maybe we don't have any good choices. Oh, this is pretty close. Dihydrogen phosphate, 6.3 times 10 to the minus 8. Very close. It was only 3.7 away. And so dihydrogen phosphate is a good candidate. Common, cheap, and not terribly toxic. So that's good. Here, dihydrogen phosphite is also a good candidate. But have you dealt with phosphites or phosphorus acid, not phosphoric? No, these aren't that common. So, skip that. This is good too. This is a tetrapyrotic acid. Pyrophosphoric acid. This is going to have K1, K2, K3, K4. But if you look at the dihydrogen pyrophosphate here, it's close. So we could use that, but is pyrophosphoric acid that common? No. This is succinic acid. This would be hydrogen succinate. Hydrogen succinate is close. But like other organics like this, it suffers from the problem of oxidation and decomposition, so we're going to avoid that. Eventually these can burn away. Hydrogen sulfite, close. But sulfurous acid is unstable. Hydrogen sulfide, this is more difficult to work with. Thiophenol is very close. Thiophenol is only 3.2 times 10 to the minus 7. That's good. So thiophenol would work. Except thiophenols, thiols they call them. Thiols are a component of skunk odor, and thiols all stink. They smell really bad. In fact, a friend of mine spilled 1 drop of thiophenol. Thiophenol is very common. Spilled 1 drop on his brand new tennis shoes and had to wrap them in multiple garbage bags to seal off the smell and threw them in the garbage. It smelled so bad. And so which one do you think looks the best? Yeah, I think dihydrogen phosphate. Let's go with dihydrogen phosphate. We're going to do a quick calculation here to see how we make this. So dihydrogen phosphate, 6.3 times 10 to the minus 8. So Ka for dihydrogen phosphate 6.3 times 10 to the minus 8, which gives us a pKa of 7.20. So if we mix the dihydrogen phosphate and its conjugate base, monohydrogen phosphate, in the 1-to-1 ratio, we get a pH of 7.20. But we don't want a pH of 7.20. What we want to do is we want to drop the pH down by 0.2 units. That means we're going to add a little bit more acid to lower the pH. And so how much is that little bit more acid? Okay, so first we looked for an acid with pKa. We found one with a pKa close to 7. Then we're going to determine the base to acid ratio. Determine the base to acid ratio required. And what we'll do is just use the Henderson-Hasselbalch. The pH is going to equal the pKa for our acid. The acid in this case is H2PO4 minus, plus the log of the base to acid ratio. The base is going to be monohydrogen phosphate. The acid is going to be dihydrogen phosphate. Okay, the required pH is 7.00. Our pKa is 7.20 plus the log of this ratio. And then we can calculate the ratio. The ratio of HPO4 2 minus to H2PO4 minus, in other words, log of base to acid is going to equal 10 to the minus 0.20. Just skipped some steps and took the anti-log. So I subtracted 7.20 from both sides and then took the anti-log of that. And so this is going to give us 0.6, what is 10 to the minus 0.2? .6309. 0.6309. All right, that's the ratio. So in other words, this is going to be 0.6309 to 1. So I need more, a little more acid than base. It's not a 1-to-1 ratio. In fact, if I had 1 part of base, I'm going to need, well, let's just flip this. So I'm going to invert this ratio, and I'm going to have 1.584, or just 1.58. And so if I have 1 part of base, I need 1.584 parts of acid. And so anything that matches this ratio will give us the correct pH. The pH is going to be 7.00. See how much time we have. So let's say I have this solution and I make it to 0.250 molar HPO4 2 minus. If I make it 0.250 molar HPO4 2 minus, what is the molarity of the H2PO4 minus in order to give us a pH of 7.00? Well, I'm going to need a little bit more acid because if I had it equal, molar, like 0.250 and 0.250, I'm going to get a pH of 7.20. And so I need a little bit more H2PO4 minus. How much more? We could figure it out. And so the molarity of H2PO4 minus is going to be, I got 0.250 molar HPO4 2 minus. And then I'm going to use the ratio there as a conversion factor. And so which way do I want to do this? Looks like I'll do it this way. I need 1.584 molar H2PO4 minus for every 1 molar HPO4 2 minus. And so if I make the base component 0.250, I have to make the acid component 0.396 2 molar. All right, so let's go ahead and do that. So the base HPO4 2 minus is 0.250 molar. The acid H2PO4 minus will be 0.03962 molar. And the pH with this ratio will be 7.00. So that's how. Now I can change the capacity. There's one other thing, buffer capacity. Buffer capacity is you can make it really dilute or you can make it really concentrated. As long as the ratio of the concentrations is the same, it'll give you the same pH. And so if you didn't have much money to buy much of this, you can make it very dilute. Let's make it 0.00250 molar of the HPO4 2 minus and 0.003962 molar for the H2PO4 minus. And so the pH is still going to be the same. The pH is going to be 7.00, but what I've done is I've lowered the capacity. And so it's a low capacity. And the capacity is, you know, the more components you have, the more this can withstand added acid or added base, because what's going to happen is if I add some HCl, the base will attack it, the HPO4 2 minus. If I add some sodium hydroxide, the acid will attack it and neutralize it. And so we want the buffer to try to maintain a stable pH even in the face of added acids and added bases. And so this is going to be lower capacity, same pH, versus I can make it higher capacity, 2.50 molar and 3.96 molar. I'm going to be limited by solubility though. You know, I can't go too high in capacity because of limited solubility. But this is also going to be pH 7.00, and this is going to be higher capacity. And so the more moles of buffer components I have, the greater the ability to neutralize the added acids and added bases. And so we'll look at an example of doing this, I guess, tomorrow. So I want to save some time for lab. So I'll stop here. The lab